All right, so this video will definitely be a little shorter. We're going to be looking at electrochemical cells that exist under conditions that aren't standard conditions, the 25 degrees Celsius, the 1 atmosphere, the 1 molar. And this would be basically once a electrochemical reaction starts to occur, we can have our reactant and product concentrations change. Um, we could also have our pressures change. If we added a component to our reaction mixture that caused our reactant concentration to decrease or increased our product concentration, we would be consuming more of the materials that we had present. And electrochemical cells are going to decrease in voltage until they reach a point where they have consumed everything that's available. So the non standard cell potential would be less than the standard cell potential. If you look at it in terms of an equilibrium expression, if you have a greater amount of products or if you have a smaller amount of reactants, that ratio of products to reactants would have gotten much larger. The Q would have been greater than 1. If we go at it from the opposite approach, where we add to the reactant concentration or we reduce our product concentration, we are going to have more materials that can be consumed, and that would cause our cell potential that's non-standard to be greater than our standard cell potential. Our Q would be smaller than 1 because we would either have a smaller numerator in the products or we would have a greater denominator in the reactants. When that ratio between reactants and products reaches a point where the value for Q is 1, then we would have a cell potential equal to our standard cell potential. Our Nernst equation allows us to relate these quantities under non-standard conditions to non-standard cell potential. E equals the standard cell potential, E0, minus RT over NF natural log of Q. R is your constant in joules, the 8.314. Temperature is Kelvin. N is your moles of electrons. And F is Faraday's constant, which tells us basically the amount of charge that is going to be transferred per mole of electrons, 96,485. Q would be your reaction quotient. And if you were at equilibrium, then you would have the Q replaced with your K. The Faraday's constant, that F, is, again, as I talked about, giving you the amount of charge that's going to be carried by a mole of electrons. And basically, cell potentials will continue to diminish until they reach equilibrium, when the standard cell is going to have a cell potential of 0. And that would be when your free energy is also 0. And it's what happens when your car batteries are dead, or your cell phone battery is dead, or your Chromebook battery is dead. We are going to be dealing with Nernst equation at 25 degrees more than we aren't. And when you are using it at 25 degrees, if we substitute in the 298 for the temperature, the 96,485 for Faraday's constant, and R is 8.314, we can get all of those numbers to end up being the equivalent of 0.0592. We cannot substitute the value in for N, the moles of electrons, because that's going to depend on how many electrons are being transferred between the oxidation and the reduction half reactions. It's because of the Nernst equation. There may be times where you do have to write a half reaction to determine that value for the number of electrons. I also want you to notice that when you are at 25 degrees, we write it in terms of log of Q versus natural log of Q. And I am not about to go through the math on that to explain why that works. Just know that when you're at 25 degrees, make sure you're using log. Okay? In this particular example, we're wanting to find what K is. So when our non-standard cell potential is 0 for the reaction that we've been using so far throughout these videos. So if we know that we are at equilibrium and that our non-standard cell potential is 0, we know that Q is actually going to be equal to K because we are at equilibrium. And so we can determine what the value of K is by plugging in the cell potential we know at standard conditions and the moles of electrons that are being transferred. If you go back and look at these two half reactions, we saw previously that 2 moles of electrons were being transferred as copper formed copper 2 plus ions, and as 2 silver ions produced 2 silver atoms. So the voltage for that half reaction was 0.462. Again, if you go back and look and when we calculated cell potentials previously, you'll see that. If we know those two pieces of information, we should be able to calculate the value for K. We mathematically combine our constants together, and then we want to take the anti-log of our log by raising both sides from the base of 10 to get K isolated. And when we do the math behind that, we see that the K is 4.06 times 10 to the 15th. I think I probably should have written it as 4. I'm looking at the math. Actually, if you go back and look at the top, you'll see the cell potential had 3 sig figs. And so that's why I had 3 sig figs in my final answer, because the number of electrons is not going to influence your significant figures. It is not a measured value. Our cell potential was very, very positive. So because it was very positive, we know that the reaction is moving from the reactants to the products. So we would expect our K to be quite large, and indeed it was. In this particular question, we're going to say that the silver concentration, maybe something was added to it, maybe a chloride, so it was able to precipitate out some of the silver ions, and it caused the silver concentration to become smaller, to 0.6 molar. We want to know what the new cell potential would be. So if we go back and look at that reaction, we see that we're reducing a reactant. And if we're reducing a reactant, that means we have less reactant materials available to continue to move forward with this reaction. With that in mind, we are not at equilibrium, so we do want to calculate the non-standard cell potential. Our equilibrium expression is going to be based on our balanced equation, products over reactants. We do not include the solids, we only include aqueous solutions and gases. We raise both the reactant and product to their coefficient. So when we go through and do the math for that, we didn't say anything about the copper changing. If it said that the reaction had proceeded and that as the reaction proceeded, the silver concentration decreased to 0.6, then you would have had to account for that with copper. But we don't have to do that in this particular scenario. So when I do the math, I get that Q is 2.8. I most likely would not have solved this through and rounded anything until I got to multiply that by 0.0592 over n. But just so you know that with the significant figures. I plug in what I know. I know the standard cell potential. I know that 2 moles of electrons were transferred. And that I see that when I combine that 0.0592 and the log of 2.8 over 2, my cell potential decreased. And that's kind of what we would have expected to have happened. We reduced our reactant concentration, so we're not going to be able to make as many products. And because of that, our cell potential will be slightly smaller, 0.449. The reaction, however, is still spontaneous, and it will continue to be spontaneous until it gets to 0 when it's at equilibrium. We've talked about how cell potential, and when you're positive, that's going to cause you to have a spontaneous reaction. So we can relate cell potential to energy by using the free energy and the moles of electrons and Faraday's constant. When you have a positive cell potential and a negative free energy, you're going to have a spontaneous reaction. There is energy that is going to be able to be harnessed from that chemical reaction and can then be used as work. When you have a non-spontaneous reaction, you would have a negative cell potential. That reaction would not occur spontaneously. You would have a positive free energy input because you would need energy to make that reaction proceed. And that would basically tell you the minimal amount of energy you would need to be able to push that reaction to go in the direction you would like it to. This is what happens when you have some sort of metal plating take place. You have to provide energy to force that reaction to become plated on top of something that it would not normally be plated on spontaneously. So again, going back to our good old copper and silver reaction, if we want to know if this reaction is spontaneous as written, you should be able to tell me it is, since we know we have a positive cell potential. but we can determine exactly how much energy is going to be generated from this reaction by taking into account the moles of electrons being transferred to Faraday's constant, the 96,485, and the voltage. Before you go, Miss Barker, how the heck can coulombs and voltage turn into joules? Remember that a volt is the same as a joule per coulomb. So the coulombs would cancel out, and that would leave you with joules. Quite a lot of joules, 89,200 to be specific. In kilojoules, that would be 89.2. And because free energy, the equation has that negative in front, that's telling us that that's how much energy would be released in theory if this reaction occurred perfectly. I did 3 sig figs in my free energy value because I had 3 sig figs in my voltage. The other 2 were constants, so they are not gonna or 2 is an exact value, and the other one's a constant. That's not gonna affect your sig figs. Okay? So yes, this reaction is spontaneous. If I flipped it, I would need 89,200 joules of energy at a minimum to make the copper ions be plated as copper metal.